Hi, and welcome to 9.1 Momentum and Impulse Introduction. In this lesson, students will be able to describe and calculate impulse and momentum. What the heck are those things? Let's talk about it. So let's start by considering this. If you exert a force over a period of time, you can change an object's velocity. Do you agree? Think of Newton's second law. If you're exerting a force on something, that means you can accelerate it, right? So you could change the velocity. The larger the force, the more you will change the velocity. Yeah, that's true, right? If you push on it harder, you're going to change the velocity more. And if you exert that force over a longer period of time, oh, interesting concept there, the more you will change the velocity. Exerting a force over a longer period of time, you push on it for longer, yeah, you're going to change that velocity more. That kind of makes sense. So critical thinking. Let's say you exert the same force over the same period of time on two different objects of differing mass. Which object will have a larger change in velocity? The more massive object or the less massive object? Pause the video and think of it. You probably can get an idea of what the answer is going to be. All right, so let's look at this example as a baseball player. And the baseball player is going to exert a force over a period of time on a ball, on a baseball, right? So even though it happens over a very short period of time, when you hit the ball, the bat is in contact with the ball for a certain period of time, and it's exerting that force, right? So let's say the force and the period of time is the same, but you have a more massive ball. Like let's say it's a huge, it's even bigger than a bowling ball, but it's much more massive. Which will have a larger change in velocity. Let's say maybe it's like a T-ball. I should have made this like a T-ball here. The initial velocity is 0, and then which is going to gain more velocity? Hopefully, you said the less massive ball will gain more velocity, and the more massive ball will gain less velocity. But it's the same force acting over the same period of time in both cases. But because the mass is different, the change in the velocity is different. And this whole idea is leading us into these concepts of impulse and momentum. So it says, and the conservation of momentum. It says, let's begin our discussion of the conservation of momentum by first defining what momentum is. Then we will see how a force acted on an object over a period of time, otherwise known as an impulse, can change that object's momentum. Just like we said, if we're changing the object's velocity, we're going to change the object's momentum by exerting a force over a period of time. We will then explore how even though an individual object's momentum may change due to an impulse, the total momentum of an isolated system is conserved. So what the heck is this saying? Well, if you have a red object coming in contact with a blue object, this is like a classic diagram here. Then they collide, boom, collision. This is a big idea, it's collisions. And then they have a different velocity. We're changing the direction of their velocity. So that means we're changing their momentum. But the total momentum, if you do the momentum of the red object plus the momentum of the blue object initially, is going to be equal to the total final momentum, meaning you take the momentum of the red object and the momentum of the blue object after the collision, then the total momentum remains the same. This momentum is equal to that momentum. Momentum is conserved. That's the big, big idea, right? And we'll get there. And actually, there's different types of collisions. You could have what's called a elastic collision and an inelastic collision, but I'm getting way ahead of myself. I just wanted to give you an overview of where we're going with this. First, let's define what momentum is. Okay, so first of all, we use a lowercase p to represent momentum. And momentum is the product of the mass and velocity of an object. Momentum is a vector quantity. If you noticed, I was using arrows in that previous example with the red and the blue ball. Those arrows are vectors, the momentum vectors. All right, so the direction matters. The formula for momentum is basically in the definition, it's the mass times the velocity. So P is equal to mv. And this velocity is where we get the vector for the momentum from. Actually, technically, we should be writing, this is like how you make vector notations on your variables. So that's kind of cool. The units. Let's talk about what our units should be. Pause the video and think about it. If you had to guess, what would you make the units for momentum given this equation over here? Well, what are the units for mass? Kilogram. And then what are the units for velocity? A meter per second. And guess what? We're not going to invent a new unit like a Newton or a joule. We're just going to keep it in terms of kilograms times meter per second. That's, believe it or not, the units for momentum. So written out, it looks a little funky. It looks like I'm subtracting. I put a hyphen there. So I want you to be able to say it. Say it with me. Kilogram meters per second. Okay? And it looks like this. You could put like a dot in the middle if you want to represent times. You don't have to. You could just do kgm/s. Kilograms times a meter per second. That's the unit for momentum. Don't forget it. Now, you might be asking yourself, why the heck would we use a P? Momentum starts with an M. Well, Newton described the concept of momentum in terms of impetus, which comes from the Latin petere, which means to go, to seek, from the Greek petistai, which means to fly. I probably did not pronounce that right. Also, push and pull derive from the Latin pellere. The real question is, why not P? Also, M was taken by mass already, so yeah, you wouldn't want to say like M, even if it's capital. M is equal to mv, like it's kind of weird. So we just use a P instead for momentum. So where is the formula for momentum? It's on the back of the reference table. Okay, P is equal to mv right here. And this is the conservation of momentum. And then tomorrow we're going to do the impulse momentum theorem. But don't get this P confused with this P. That's for power, and it defines them right here for you if you would like. Okay, if you forget. So let's do an example here. It says a pitcher claims he can throw a .145 kilogram baseball with as much momentum as a speeding bullet. Assume that a 3-gram bullet moves at a speed of 1,500 meters per second. That's a pretty wild claim this pitcher's making, that they could throw a baseball with the same momentum as a bullet. How fast would that ball have to be traveling? That's what question A is saying. What must the baseball's speed be if the pitcher's claim is valid? And then which has a greater kinetic energy, the ball or the bullet? This is a screenshot, by the way, from a video that's in the extension folder if you want to check it out. It's of a baseball player throwing a ball at 105 miles per hour. So I wonder if that's fast enough to have the same momentum as a bullet. Let's find out. All right, so we have two different objects here. We have a baseball and we have a bullet. It would be helpful to define them as A and B because the ball and the bullet both start with B. So in the subscripts, the mass of the baseball, MA, is 0.145 kilograms. The mass, the velocity of the ball is what we're looking for. The mass of the bullet is equal to 3 grams, which is equal to, we want to multiply by a conversion factor here. 1 kilogram is equal to how many grams? Pause the video, think about it. 1,000 grams. So that's 3 times 10 to the negative 3 kilograms. It's a tiny bullet, but it's moving very fast. it has a muzzle velocity of 1.5 times 10 to the third meters per second. So yeah, how fast does that have to be so that the momentum of the ball is equal to the momentum of the bullet? All right, you could do this a couple different ways. First, let's figure out what is the momentum of that bullet, and then we'll use that momentum to find the velocity of the ball, just as like some practice with this new equation. So the momentum of the bullet is the mass of the bullet times the velocity of the bullet. So you plug in the values for the bullet, and then you could actually do this in your head if you remember the rules for the exponents. If you add -3 plus 3, those go away. So 3 times 1.5 is 4.5. So the momentum of this bullet here is 4.5, but 4.5 what? What are the units for momentum? It's a kilogram times a meter per second. So we just write kilogram meters per second. That's how you do that, okay? So yeah, we want to say, okay, this person's saying the momentum of the ball is equal to the momentum of the bullet. Well, if that's true, how fast does it have to be? All right, so this is the momentum of the ball. That's equal to the mass of the ball times the velocity of the ball. Now we already know, okay, how fast do you have to have this momentum? The momentum of the bullet, 4.5 kilogram meters per second. If the baseball is 0.145 kilograms, right, how fast do you have to be traveling? So you do the division and you find out that the velocity of that ball only has to be about 31 meters per second, much slower than the velocity of the bullet because the mass of the bullet is so tiny in comparison to the mass of the ball, right? So to have the equal momentum, all right, it depends on the mass and the velocity. Well, is that possible, right? So how many miles per hour is this? Just as a quick review, if you have a 31 meters per second, let's set up our conversion factor just for fun, right? We want to get rid of meters and go into miles. So 1 mile is actually equivalent to 1609 meters. I remember that because that's the year I was born. And then you multiply by another conversion factor to get rid of the seconds. Now the seconds were on the bottom over here, so we want to write the seconds on the top over here, and we want to go into miles per hour because that's how we measure the speed of baseballs, right? So 1 hour is equal to 3,600 seconds. You do that, multiplication and division, so the seconds will cancel out. The meters will cancel out. You're left with miles per hour. You do 31 times 3,600 divided by 1609, and you get about 69 miles per hour. That is not that fast when you're talking about baseball speeds. Like, I'm pretty sure that you could probably throw that fast. You could throw a ball as pretty close to the same momentum as a speeding bullet being shot from a gun. That's pretty crazy. But remember, when we're talking about momentum, you have to talk about the mass and the velocity. So speaking of velocity, which has a greater kinetic energy, the ball or the bullet? Well, the kinetic energy is equal to 1/2 mv squared. Ooh, so the velocity is going to have like it's squared, so it has more of an impact on the kinetic energy. So which one do you think is going to have a greater kinetic energy? Or are they going to be equal since the momentums were equal? Well, I'll do the math for you, and we'll see if your prediction is correct. So this ball only has a kinetic energy of 69.7 joules, whereas the bullet has a whopping 3,375 joules of kinetic energy because, again, the velocity is moving super fast and that quantity is being squared. So kinetic energy, different from momentum, even though they both have to do with the mass and the velocity. All right, but in kinetic energy, don't forget the velocity is being squared. All right, time for you to try it out. pause the video and answer the question. It says a 1,950 kilogram car is traveling down a highway with a momentum of 4.8 times 10 to the 4 kilogram meters per second. What is the speed of the car? Did you figure it out yet? Pause the video. Figure it out. All right, hopefully you figured it out because there's even more. Now that you know the speed of the car initially, what happens when the driver steps on the brakes and decreases their speed to 15 meters per second? What is the car's new momentum? And what was the change in the momentum? Pause the video and figure that out. You could do it. It's a little weird, but you could do it. Come on, pause it. Figure it out. Okay, let's start by writing the given information, the unknown, write your equation, substitute, and when you solve, you get a velocity of 24.6 meters per second. So this car, in this problem, is the first one traveling at 24.6 meters per second. Then they step on their brakes and decrease their speed to 15 meters per second. So all of a sudden, this was your initial velocity, and your final velocity is 15 meters per second. They're saying, what is your new momentum? What is the final momentum after you step on the brakes? So that means that this was your initial momentum. They want to know what your final momentum is. Use the same equation, substitute in, but now we know the velocity is 15 and we want to know what the final momentum is. And that's going to be 2.9 times 10 to the 4 kilogram meters per second, or 29,250 to be exact, right? Then it says, what is the change in momentum? So remember, change, we use the delta symbol to represent change. The change in momentum is what we want to know, right? So we could actually make a little formula here. The change in the momentum is equal to the final momentum minus the initial momentum. That'll tell you how much you changed your momentum by. So you substitute in. And if you do final minus initial, you end up getting a negative number. Now remember, momentum is a vector quantity, so the negative does represent the direction here. So the negative 1.9 times 10 to the 4, and we could say kilogram meters per second. We were traveling to the right with an initial momentum, and then that momentum decreased, trying to make the vectors like this is a larger vector, that's a smaller vector. So the momentum decreased because you pressed on the brakes, exerting a force in the opposite direction, slowing you down, which is why the change in the momentum is in the negative direction. Now it's helpful to have a concept for this change in momentum and the idea that you're exerting a force over a period of time. Okay, that concept is called impulse. Impulse is the change in momentum. Impulse is a vector quantity, as we saw with that negative sign. All right, so the units for impulse are actually going to be a Newton second, and the formula looks like this. If the impulse is the change in the momentum, that means J is equal to delta P. And most of the time, if you're changing your momentum, it's not because you're changing your mass. It could be. You could definitely change your mass in certain situations. But most of the time, it's because you're changing your velocity. So that's why we can expand this out to m delta v. We're going to talk about impulse more tomorrow when we do the impulse momentum theorem. But for now, we'll just say that if you change your momentum, it's because an impulse was imparted on you. So why J, impulse starts with an I? Well, just because that's why impulse is a J, because physics. So let's do it. Another example here. You could do it. It says a 975 kilogram car is traveling at 25 meters per second. It applies its brakes, slowing it down to 8 meters per second. What is the car's initial momentum? what is the final momentum, and then what is the impulse exerted by the car's brakes. For now, we're just talking about impulse in terms of a change in momentum. But tomorrow, we are going to say how, the impulse is actually the force exerted over a period of time. Both things, the force and the time, have to do with the impulse. But again, for now, what's the change in momentum? We could say that's equal to the impulse. Did you pause the video and do the question on your own? Because here are the answers. Here's the givens. These are the unknowns. I will substitute, actually, I'll write the equation. I'll do both at the same time because they're pretty similar. You substitute in the values, and when you solve, you get an initial momentum of, let's keep it long here, 24,375. What are the units for momentum? Kilogram meter per second, okay? And then for the final momentum, you get 7,800 kilogram meters per second. So you're decreasing your speed, you're decreasing your momentum. How much did you decrease your momentum by? What was your change in momentum? So we could write this formula again. The change in the momentum is equal to PF minus PI, right? Substitute in. And then when you solve, you do get a negative number, and that's on purpose, right? That shows the direction of the impulse is 16,575 kilogram meters per second. All right, that's the change in the momentum. Oh, but it specifically said what is the impulse exerted by the car's brakes. So actually, we can use this as the impulse because we said that the impulse is equal to your change in the momentum. So technically, I should have wrote that first, and then I could have wrote this. And then you get an impulse. What is the J? See, I wrote it wrong over here. I should have said, what is the impulse, J? Even though by definition, it is the change in momentum, but that's all right. We'll say the impulse is equal to negative 16,575. What did we say the units for impulse were? We said a Newton second, which seems weird right now, but tomorrow again we're going to see how force and time, a Newton and a second, are used to define impulse. Because how did you slow down? With your brakes, you had to exert a force over a period of time, right? And in doing so, you changed your momentum. Okay, so is a Newton times a second really equivalent to a kilogram meters per second? Let's see. You could write a Newton second, Newtons times seconds, and remember a Newton force is equal to MA, F equals MA, so a kilogram times a meter per second squared times seconds. Seconds cancel out. What are you left with? A kilogram times a meter per second. So a Newton second is equivalent to a kilogram meters per second. Impulse is your change in momentum. And then tomorrow we're going to say, oh, it's equal to the force times time. Beautiful. That's about it. Thanks for watching and have a great day.